Hello, good day everyone. Welcome to our astronomy class. We will discuss about the ancient astronomy. Astronomy around the world. Ancient Babylonian, Assyrian, and Egyptian astronomers knew the approximate length of the year. The Egyptians of 3,000 years ago, for example, adopted a calendar based on a 365-day year. They kept careful track of the rising time of the bright star Sirius in the pre-dawn sky, which has a yearly cycle that corresponded with the flooding of the Nile River. The Chinese also had a working calendar. They determined the length of the year at about the same time as the Egyptians. The Chinese also recorded comets, bright meteors, and dark spots on the sun. Later, Chinese astronomers kept careful records of guest stars, those that are normally too faint to see but suddenly flare up to become visible to the unaided eye for a few weeks or months. We still use some of these records in studying stars that exploded a long time ago. In Britain, before the widespread use of writing, ancient people used stones to keep track of the motions of the sun and moon. We still find some of the great stone circles they built for this purpose, dating far back as 2800 BCE. The best known of these is Stonehenge. Our concept of the cosmos, its basic structure and origin, is called cosmology, a word with Greek roots. Before the invention of telescopes, humans had to depend on the simple evidence of their senses for a picture of the universe. The ancients developed cosmologies that combined their direct view of the heavens with a rich variety of philosophical and religious symbolism. At least 2,000 years before Columbus, educated people in the eastern Mediterranean region knew Earth was round. Belief in a spherical Earth may have stemmed from the time of Pythagoras, a philosopher and a mathematician who lived 2,500 years ago. He believed circles and spheres to be perfect forms, and suggested that Earth should therefore be a sphere. As evidence that the gods like spheres, the Greeks cited the fact that the moon is a sphere. The writings of Aristotle, the tutor of Alexander the Great, summarize many of the ideas of his day. They describe how the progression of the moon's phases, its apparent changing shape, results from our seeing different portions of the moon's sunlit hemisphere as the moon goes by. Aristotle also knew that the sun has to be farther away from Earth than is the moon because occasionally the moon passed exactly between Earth and the sun and hid the sun temporarily from view. We call this a solar eclipse. The key to natal astrology is the horoscope, the chart showing the positions of the planets in the sky at the moment of an individual's birth. The word horoscope comes from the Greek words hora, meaning time, and scopus, meaning a watcher or marker. So horoscope can literally be translated as marker of the hour. When a horoscope is charted, the planets must first be located in the zodiac. At the time astrology was set up, the zodiac was divided into 12 sectors, called signs, each 30 degrees long. Each sign was named after a constellation in the sky through which the sun, moon, and planets were seen to pass. The sign of Virgo after the constellation of Virgo, for example. When someone today casually asks you your sign, they are asking for your sun sign, which zodiac sign the sun was in at the moment you were born. The birth of modern astronomy started with Copernicus, when he discovered Heliocentric, which concluded that Earth is a planet and that all the planets circle the sun. This illustration shows the Copernican heliocentric theory. With his telescope, Galileo was able to carry out the test of the Copernican theory mentioned earlier, based on the phases of Venus. Within a few months, he had found that Venus goes through phases like the moon, showing that it must revolve about the sun, so that we see different parts of its daylight side at different times. Galileo also demonstrated a telescope with a magnification of 9 times 2 government official at the city-state of Venice. This picture shows the first telescope used by Galileo. According to him, if Venus circles the Sun, the planet should go through the full range of phases just as the Moon does, whereas if it circles Earth, it should not, as shown in this figure. Also, we should not be able to see the full phases of Venus from Earth, because the Sun would then be between Venus and Earth. But in those days, before the telescope, no one imagined testing these predictions. Now let us proceed to orbits and gravity. At about the time that Galileo was beginning his experiments with falling bodies, the efforts of two other scientists dramatically advanced our understanding of the motions of the planets. These two astronomers were the observer Tycho Brahe and the mathematician Johannes Kepler. Together they placed the speculations of Copernicus on a sound mathematical basis and paved the way for the work of Isaac Newton in the next century. Brahe made a continuous record of the positions of the Sun, Moon, and planets for almost 20 years. His extensive and precise observations enabled him to note that the positions of the planets varied from those given in published tables, which were based on the work of Ptolemy. Brahe found a most able young mathematician, Johannes Kepler, to assist him in analyzing his extensive planetary data. Through his analysis of the motions of the planets, Kepler developed a series of principles, now known as Kepler's three laws, which describe the behavior of planets based on their paths through space. The first two laws of planetary motion were published in 1609 in the New Astronomy. Their discovery was a profound step in the development of modern science. The laws of planetary motion. Kepler's first law states that each planet moves around the Sun in an orbit that is an ellipse, with the Sun at one focus of the ellipse. Second law says that the straight line joining a planet and the Sun sweeps out equal areas in space in equal intervals of time. The third law states that the square of a planet's orbital period is directly proportional to the cube of the semi-major axis of its orbit. The path of an object through space is called its orbit. Kepler initially assumed that the orbits of planets were circles, but doing so did not allow him to find orbits that were consistent with Brahe's observations. Working with the data for Mars, he eventually discovered that the orbit of that planet had the shape of a somewhat flattened circle, or ellipse. Next to the circle, the ellipse is the simplest kind of closed curve, belonging to a family of curves known as the conic sections. Kepler's second law deals with the speed with which each planet moves along its ellipse, also known as its orbital speed. Working with Brahe's observations of Mars, Kepler discovered that the planet speeds up as it comes closer to the Sun and slows down as it pulls away from the Sun. He expressed the precise form of this relationship by imagining that the Sun and Mars are connected by a straight, elastic line. When Mars is closer to the Sun, as in positions 1 and 2, the elastic line is not stretched as much, and the planet moves rapidly. Farther from the Sun, as in position 3 and 4, the line is stretched a lot, and the planet does not move so fast. As Mars travels in its elliptical orbit around the Sun, the elastic line sweeps out areas of the ellipse as it moves. Kepler found that in equal intervals of time, or denoted by t, the areas swept out in space by this imaginary line are always equal. That is, the area of the region B from 1 to 2 is the same as that of region A from 3 to 4. If a planet moves in a circular orbit, the elastic line is always stretched the same amount and the planet moves at a constant speed around its orbit. But, as Kepler discovered, in most orbits that the speed of a planet orbiting its star tends to vary because the orbit is elliptical. In 1619, Kepler discovered a basic relationship to relate the planets' orbits to their relative distances from the Sun. We define a planet's orbital period, or P, as the time it takes a planet to travel once around the Sun. Also, recall that a planet's semi-major axis, A, is equal to its average distance from the Sun. The relationship now known as Kepler's third law says that a planet's orbital period squared is proportional to the semi-major axis of its orbit cubed. When P is measured in years and A is expressed in a quantity known as an astronomical unit, or AU, these two sides of the formula are not only proportional but equal. 1 AU is the average distance between Earth and the Sun and is approximately equal to 1.5 times 10 to the power of 8 kilometers. In these units, P squared is equals to A cubed. Kepler's third law applies to all objects orbiting the Sun, including the Earth, and provides means for calculating their relative distances from the Sun from the time they take to orbit. Now, let us take a look at a specific example to illustrate how useful Kepler's third law is. How do we calculate periods? Let us have the following example. Imagine an object is traveling around the Sun. What would be the orbital period of the object if its orbit has a semi-major axis of 50 AU? From Kepler's third law, we know that when we use units of years and AU. How do we calculate periods? Imagine an object is traveling around the Sun. What would be the orbital period of the object if its orbit has a semi-major axis of 50 AU? From Kepler's third law, we know that when we use units of years and AU, P squared is equals to A cubed. If the object's orbit has a semi-major axis of 50 AU, or A is equals to 50, we can cube 50 and then take the square root of the result to get P. So we have P is equals to square root of A cubed. P is equals to square root of 50 times 50 times 50, which is equals to square root of 125,000, or 353.6 years. Therefore, the orbital period of the object is about 350 years. This would place our hypothetical object beyond the orbit of Pluto. Alright, well, I guess that's the end of our session. I hope you learned something. Hope to see you soon. Bye!